Okay, this is the 13th video for this linear algebra series. So today we have the following goals. We will cover orthonormal basis, and associated with this topic are the following: named theorem and procedure. First is the Gram-Schmidt procedure. The second is Shor's theorem. And third is Riesz Representation Theorem. Last time we have started our discussion on inner product spaces, basically defining what an inner product is, finding norm, and then discussing properties, basic properties of norms, and what else? We also have some famous inequality from your calculus in their analog when we are phrasing them in the language of norms, the Cauchy-Schwarz inequality and the triangle inequality, and also the Pythagorean theorem. We also discuss concepts of orthogonality and then the concept of vector projection. So decomposing vector with what we call the orthogonal projection. So writing a vector u, a scalar multiple of a vector v times plus a vector orthogonal to v. So we call that an orthogonal projection. Now we have the following. We will start with orthonormal basis. Let's start today's discussion with definition of orthonormal basis. Orthonormal basis. So this is covered in B of chapter 6 of Axler. So let us define first an orthonormal basis. We shift to ball pen. So first, we will have orthonormal list of vectors. So we call it an orthonormal if we call the list or orthonormal list of vectors if let's say let's name this S. S is an orthonormal. Okay, let me rephrase the statement. So we have a list of vectors, of course, is orthonormal. If each vector has norm 1, first is norm 1, and second condition is is orthogonal to all other vectors in the list. So to make this precise, if we have EU, let's call E1 to EM be the list, then the inner product of E1, EJ, okay, let's be consistent with the notation. Let's call this J and then let's call this K. EJ and EK has the following formula. This is equal to 1 or 0. 1 if J is equal to K. And here J is not equal to K. 0. So let us consider examples. First example is the standard basis. So in F, say 2, standard basis is an orthonormal list. I will abbreviate the orthonormal like that. So let's recall this is 1, 2, and 0, 0, 1, and 1, 2. And then, of course, we can extend to standard basis of F to the N. And then this is an orthonormal list. And the other one is the following. This is 1 square root of 3, 1 square root of 3, 1 square root of 3, and then the other one is negative 1 square root of 2, and then 1 square root of 2, and then 0. Okay, this list has two elements, and verify that if you take that product of these two elements, here A and B, you get 0. And of course, if you look at the norm of each of these first vector and the second vector here, is just 1. I think you get the grasp of what an orthonormal list is. Let us now consider a proposition which I usually referring as theorem from before. So if we have your E1 to EM, or the normal list, so of course of vectors in V, then your A1 E1 plus up to A N E M, get the norm of this is just equal to A1 squared, absolute value of A1 up to AM squared for all the A sub I in the field, the base field F. The proof here is direct. Note that E sub I has norm 1, and then apply repeatedly the Pythagorean theorem. I will not show that very explicitly. Now we have an obvious result regarding the list being orthonormal, which follows from the fact that if the A sub 1, the absolute value up to A sub m is 0, we will get the A sub j is 0 as well, giving us an orthonormal, the orthonormal list being linearly independent. So let me state this as a theorem. If our E1 EM is an orthonormal list, then E1 to EM is linearly independent. When I say is here, I'm referring to the list, not the individual vectors. No, it's not a proof, it's a statement. Then this is very one-liner proof. Now let us define what we call an orthonormal basis. Basically, if we have an orthonormal list, we can define also the concept of orthonormal basis. So, of course, this is a basis where every vector is of norm 1, and then normal, orthonormal, other vectors. So here an orthonormal is orthonormal. Okay. Oh, what is this? An orthonormal list or basis of B is an orthonormal list in V that is also a basis. And this is there's another result here that is very obvious. If we have an orthonormal list of right length, then we have an orthonormal basis. So if the orthonormal is, if an orthonormal is of length n, which is equal to the dimension of the vector space V, then this list is an orthonormal basis. This theorem is very easy. Just think a bit. So if you have the same dimension, then they basically this basis is basically a basis for same vector space. All right. Okay, let us consider an example. In this case, this is a book example. If we have one half, one half, one half, one half, then one half, one half. The other one is one half, one half. The other one is this is each, let's call this V1, VI is of norm 1, and if VK is 0, no, is just 0. Our I here, let me call it J not equal to K. So here, if this in this, you get 0. So you can check if this one you dot product it, or we take the inner product of this and this here, alternating signs, so you get 0, and then in the same way for the rest. Okay, because there are 4. The cardinality of this list is 4. Okay, let me write. Cardinality is 4, and then cardinality of the list, or the length of the list, is equal to the dimension of F4, and say the list is, this list is an orthonormal basis. Okay. Now, in general, if you have a vector, if you have in general, so suppose we have arbitrary basis. So let's call this E1, En, bases of our vector space V. Of course, if we have a vector in V, then V is just a linear combination of its linear combination of the basis elements. And the question is, the compute your A sub I with respect to arbitrary basis is hard, and then it's easy if we get here the term is arbitrary, it's hard. It's easy if we have an orthonormal basis, which I will give as a theorem here. So if we have an orthonormal basis, if we have E1, EM, orthonormal basis of our vector space V, and you have a vector in V, then we can write your vector V as follows. You have V E1 and then E1 plus V tapos En and then En. And also the norm of our V squared is just V1, VE1, then you get that squared up to VEN, then you get that squared too. So the second part here is direct from our theorem earlier. That is a repeated application of Pythagorean theorem. The first one is we will prove the first statement here. Proof. So we will write V as A1 En, linear combination of the bases of V, the orthonormal basis. Because this is orthonormal, then if we get V and then that product it with inner product of V with EJ, so V and then EJ, you get V here and then wait. And the same here, we get A1 E and then dot AN EN and then that product inner product it with E sub J, you get here, you get A sub J, since we just have E sub J is 1 else 0, A sub this is inner product. This is the reason J and K is 0, J not equal to K. Okay. So that means that your coefficient of E sub J is just A, the inner product of V, together with the base ordered basis element E sub J. And then this star here follows from our previous result. Basically, the result given which result? The result here. So that's it. Now we will go to, you already have that theorem. if we understand the usefulness of the orthonormal basis, because your orthonormal, the coefficient will be just the inner product of the vector together with the orthonormal basis element E sub 1 or E sub I will give you the coefficient A sub I. Now, how do you get the orthonormal basis? So this is due to Jürgen Gram, and then he's a Danish mathematician, and the other one is L13 in, of course, it sounds German, and they call this later on the Gram-Schmidt process, or sometimes Gram-Schmidt procedure, or whatever word for procedure. Depends on the reference. Here we will call it the Gram-Schmidt procedure. So this is basically how to find, and given an arbitrary basis, how can we derive or get an orthonormal basis from it. So, but we will do it in the context of an independent list, and then extend this later on when we will construct an orthonormal basis. So let us consider now. This is called the Gram-Schmidt process or procedure, and then this is written as follows. Suppose that we have V1 to Vm, and then this is linearly independent. As I mentioned, independent earlier, I will consider it for list of vectors, and then we will derive a linearly independent orthonormal list, or I mean an orthonormal list. Okay, vectors in V. Let us construct inductively. So first, our orthonormal list of vectors. So first, we will define E sub 1 to be the vector V1 divided by its norm V sub 1, norm of V1. And then for the following, for J from 2 to M, we define E sub J inductively. I will define E sub J inductively as follows. So I will use the third edition of the book here. E sub J is just the following. We have V sub J minus the inner product of V sub J and E sub 1, and then E1 minus up to V sub J, and then the inner with respect inner product with E sub J minus 1, and then times E sub J minus 1, and then we divide it all with the following. So divide it with the norm of the numerator. So basically, we're taking the norm of everything here. Now let me write that out. So here we have V sub J minus the inner product. So the inner product is just a scalar. A sub J minus 1, and then J minus 1, and then you take its norm. And then what we have is a collection or a list, E sub 1, E sub 2 up to E sub M. Here we have an orthonormal list of vectors in our vector space V, such that the span of the list is equal to the span of the obtained orthonormal list. such that your span of V1 to Vm is equal to the span of the obtained orthonormal list E1 to Em for our inductive variable 1, j from 1 to our M. Okay, so maybe it's good to look at the proof quickly, and then I will just not write it in full, but I will tell you how it's done. So we will use induction on J. Now for the induction, we will start with the base case for our J equal to 1. Then your span of your we have for J equal to 1, span is easy to show that the span of V1 is just equal to the span of our E1 as E1 here is just V1 over this the norm of so that means, and this means that E1 is 1 over the norm. So E1 is multiple of V1. When I say multiple, I'm referring to scalar multiple. Now, hypothesis of induction. Suppose that for our 1j up to m, span of v1 to v sub m, wait, j minus 1 is equal to the span of e1 up to e sub j minus 1. This is our supposition. We have to know that your v sub j is not in the span of v sub 1 up to v sub j minus 1, since v sub 1 to v sub m, v sub I are linearly independent from I1 to m. Thus, we get v sub j is also not in the span of e sub 1 to e sub j minus 1. Hence, we are not dividing by 0 in the definition of E sub g, and dividing a vector by its norm produces a. Okay. We are not dividing by 0. And then if you divide a vector by its norm, you produce a vector of norm 1. And thus, your E sub j as norm 1. So this is obvious. So let us consider the following. From k from 1 to j minus 1, then your inner product of a sub j and e sub k is equal to, let us write what we have earlier. So this is v sub j minus v sub j e1 minus up to v sub j, and then e sub j minus 1, and then over v sub j, the same, v sub j e1 E1, and then up to V sub J, E, J minus 1, E, J minus 1. Then dot product inner product with E sub K. How do I do this? Then norm. So if you have inner product, then here we can expand the following. We know that the norm is just copy the norm. Okay, and then we distribute E sub K by property of inner product. So V sub K that product with E sub K, this part here, and this part, and then this part or everything with E sub K, we will just get our all the rest will become 0 except the one with K as subscript. So we have E sub K here. Notice that this part are the same. So we get, okay, we get here 0. Thus, what can you say about this E sub J and E sub K? You get, we get E sub 1 up to E sub J is an orthonormalist. If of vectors. Now, so from this definition, we see that, so here V sub J now is an element of the span of E sub 1 to E sub J. Okay? And then combining this information, we get the span of V sub 1 to V sub J must be inside or included in the span of E sub 1 up to E sub J. And because there are J of them, and then they are linearly independent, and then here we have linearly independent, and they are the same length, then we say that the span of V sub 1 to V sub J is equal to the span of V sub 1 up to V sub J, completing the proof. All right. Okay, this is fairly abstract. So I think we need to get our hands familiar with like examples. Okay, the example here is quite long. So I will leave some of the computations as exercise. So let us consider our space of polynomials degree at most 2, and then define the product EQ by the integral from -1 to 1 of EQ. Then we will apply the Gram-Schmidt process, and then with a standard basis for the polynomial 1x squared. So here we will write this V1, write this as V2, and write this as V3. And then find an orthonormal basis. Basis for of our E2R. Here we will just apply our formula. Solution. The first one is you need to get our V sub 1 is just 1. Of course, your E sub 1 here is just what? V sub 1 over the norm of V sub 1. Your norm V sub 1 squared is just the integral from -1 to 1 of 1 squared dx, which gives us 2. And therefore, here it's just 1 over square root of 2. Okay. So this is our E sub 1. For E sub 2, okay, for E sub 2. So, we have E sub 2 is just, we compute first your x. X minus x minus E1 and then E1. Then we have x minus the integral from -1 to 1 of x square root of 1 over 2 dx times 1, 2. So here we get x minus, it's just x squared, no? It's 1 over 2 integral -1 to 1 of x dx. This is x minus 1 half. And then x squared, and then we get over 2, -1 to 1. Here we get 1 minus 1, so we have 0. Okay. We just have x, but we will look at the norm of our x here. The norm of x squared is just the integral from -1 to 1 of x squared dx, which is just 2/3. Thus, your E sub 1, E sub 2, I mean, is just x over the norm. Here, this means that this x here is just square root of 2 over 3. So this is just square root of 2 over 3, or this is square root of 3 halves x. So we have E sub 2. And lastly, for our E sub 3, how do we compute for E sub 3? First, we get x squared minus our, this to be sub 3, x squared, x squared E1 minus x squared E2. So here we get x squared minus the integral from -1 to 1 of x squared square root of 1 over 2 dx, then 1 over square root 2 minus this integral -1 to 1, and then x squared, and square root of 3 over 2 x dx, and then we get square root of 3 over 2x, and here this is equal to x squared first, and then And this part here, we get x to the fourth, and that is an even function, so x to the fourth over sum, and then you get this part will become 0. And this part here, we get x. This is just 1/3. Here we get x raised to 3 over 3. And then we get, let us compute this. This is 1 over 2. Let's raise first and then show this explicitly. This one, I will leave it as exercise to be 0. So this is 1/2. Then the integral from -1 to 1 of x squared dx. This is x squared and then 1/2. And x raised to 3 over 3 and then -1 to 1. Then this is just x squared minus 1/2. And then here we get 1/3 minus -1, positive 1/3. So here we have x squared minus 1/2 times 2/3. We get x squared minus 1/3. However, now we want to look at x squared minus 1/3. Its norm. So its norm is just, how do you compute this? The integral from -1 to 1 of x squared minus 1/2. And then, or minus 1/3, I mean, what minus 1/3 squared dx. This is just -1 to 1 of x to the fourth minus 2/3 x squared plus 1/9 dx, and then it's a long computation, and it will give us 8 over 45. So verify exercise. So 8 over 45, thus your e sub 3 here will be, this means that this x squared minus 1/3, its norm is just square root of 8 over 45. So 8 square root of 45 over 8 times x squared minus 1. Thus, an orthonormal basis for our P2R is, first we get 1 over square root of 2. The second one is 3 over 2 square root times x. And then third one is square root of 45 over 8 times x squared minus 1/3. So we have, this is our E1, this is our E2, this is our A3. And then, yeah, that's it. This is an orthonormal basis for our P2R. Now, let us consider an existence theorem. Every finite dimensional vector space has an orthonormal basis. The proof here is apply the Gram-Schmidt procedure to basis of our vector space B. And then you get an orthonormal list, and then extend this orthonormal list to an orthonormal basis. No. Producing an orthonormal list with the same length as B, the dimension of B, and then you that list which is orthonormal will become the orthonormal basis. And then the next theorem, if we have suppose that our vector space B is finite dimensional, and then the result is then every or orthonormal basis no, orthonormal list can be extended to an orthonormal basis. I will quickly write the outline of the proof here. It's as follows. We have E1 to EM, orthonormal list. Of course, if you have, they are linearly independent. So extend to a basis. You have E1, EM, and then V1 to Vn of the vector space V. Now we have basis. Apply the Gram-Schmidt procedure to this basis. To this basis, so that we get E1 and then EM, F1 to Fn. The orthonormal. On the orthonormal basis required. Okay. Now, if the next result is, I will just write it in as follows. If we have an upper triangular matrix, upper triangular with respect to our basis, then we have an matrix T, which is also upper triangular with respect to orthonormal basis. Some orthonormal basis of our B, So I will leave this as exercise. And then now I will state a special case. This is called the Riesz theorem. The context here is you have a vector space over C. So here V is a finite dimensional complex vector space. And then we get a linear operator on V. Then our T has an upper triangular matrix with respect to some orthonormal basis of our vector space. So the proof here, if we have a complex vector space and we have a linear operator, then this linear operator T has an upper triangular matrix with respect to some bases, and from the theorem above, it also has an upper triangular matrix with respect to the upper respect to the orthonormal basis. Now let's go back to linear functionals. To recall linear functionals. So this is just a linear functional is just an element of an linear map, the set of linear maps from V to our F. So please recall this is provided in the previous video. Now, if you have a vector u and the map that sends you, if you have our vector u on the space V, and then you get V here, and then sends it to V inner product with U. This is a linear functional. And then because here V is an element of V and V inner product with U is a scalar or element of F. The next result shows that every linear functional on V is an inner product with respect to a unique U. So this is called a Riesz Representation Theorem. Okay. So here, the power, we will have the following example, and then this example will show that the linear functional, there's no obvious candidate for U. So basically, this is hard to find this U. This is not obvious, but this is a clever result from Riesz. And then this is coming from the following theorem. Let us write that. Call this the Riesz Representation Theorem. And here there is just an existence of this unique vector, but in the proof we will provide what really is this unique vector. We will provide a construction of this vector U. Suppose that your V is finite dimensional vector space, and we get a linear functional on our V. Then there is a unique U. Of course, U is in V, such that your linear functional evaluated at V is equal to the inner product of V with U here for every V in the vector space. All right, this is a nice result, so it's worthy to prove in the video. So let's start the proof. The first is we show the existence of such U. Okay, so let us consider E1 to E sub M be an orthonormal basis. So here we are assuming that we have an orthonormal basis. Of course, we can do this by Gram-Schmidt process. Then look at the functional applied to V. So this is just because we have we can represent V as follows. This is just, we represent V as V E1 and then E1 up to V E M E M. Here, these are our scalars. Of course, because of the property of being a linear map of our linear functional, we can put our V E1 outside and then get the linear functional applied to the basis elements, the orthonormal basis elements E sub. Okay. Of course, what can you do? What can you observe? Okay. Okay. So here we can okay, I'll remove this part here. It's not part of just emphasizing something. We can put this everything inside our V here, and then we have apply via what? Property of inner product. So we get this one, then the conjugate of this is just conjugate of e sub 1 times e sub 1 plus up to conjugate of e sub m times e sub m. Okay, so this is basically in for the homogeneity, ano nga, the property on, let me check, what's the proper name? This is on the basic property letter E, okay, on 6.7. All right. Okay. Because of that, okay, I think I zoomed in. Because of that, we have your linear function applied to V, which is equal to V here and U for every V in the vector space V, where our U is just this expression. So this is not trivial, not obvious how you get this. And then, okay, this is what we need for the existence. Now, we claim that U is unique. So to prove that, so this is uniqueness. Suppose that your U1 and U2 are elements of V such that your this linear function applied to V is V U1 and then equal to V U2, right? This is for all V in the vector space. Then what can you say? 0 is equal to V U1 minus V U2. Basically, this is equal to V U1 minus U2 for every V in the vector space. Now, take V equal to U1 minus U2. That this shows then your u1 minus u2 is just what? u1 minus u2 is just 0. This means that u1 must be equal to u2, completing the proof of the uniqueness of our u. Now, to end today's recording, let us apply this to uh, our previous example. So this is very common. They can encounter this in your real analysis courses. So here, find u in P2R such that your integral 1 of p t cosine of phi t dt is equal to -1 to 1 e t u t for every t in P2R. Okay, so let's quickly finish this recording by doing this example. All right. So we want to find such u. To do this, we will make P2R into an inner product space. So we define PQ as just the integral on the what? On the right hand side. So this is just the integral from -1 to 1 PQ. Okay. Note that the left side of the equation does not equal the inner product in P2 and the function t mapped to cos pi t, because this function is not polynomial. Okay, this function is not a polynomial. Now we want to find q, which is a polynomial. Okay, so define a linear functional. Our linear functional P2R to R as follows. So this is applied to P. It's just the integral from -1 to 1 of P of t cosine pi t dt. So this is our inner product. This is our linear function. Okay. Okay. For each P in P2R. Okay. Now, use the orthonormal basis. So last time, basis. So what's our orthonormal basis? So 1 over square root 2. And the other one is square root of 3 over 2x. And then the other one is square root of 45 over 8. And then x squared minus, what's that? 1/3. This is our orthonormal basis. And then how do we find q of x? So q of x here, recall that q earlier is just equal to, what is that? Let us go back. So here, instead of q, we use v. So this is just the linear functional that its conjugate applied to e1 times e1 plus here we have the linear functional, the conjugate of linear functional applied to e2 and e2, and then the linear functional conjugate of that applied to e3 and then e3. But the conjugate when we have real vector space is just the same. So we have the following. This is just the integral from -1 to 1, and then apply it to our first basis. So square root of 1 over 2 cosine of pi t dt, and then multiply it with the base element. This is 1 over square root 2 plus the integral again from -1 to 1 of square root of 3 halves x cosine of pi t, then multiply that with square root of 3 over 2x. Okay. And then lastly, we get -1 to 1, and then we apply the linear functional to the third basis element. So this is square root of 45 over 8, and then 1 minus x squared minus 1/3, and then cosine pi t. So instead of x, we use what? We use t here. Then dt, and then multiply that with square root of 45 over 8, and then x squared minus 1/3. And this is a lot of computation, and then we will get eventually, please check, q of x will be the polynomial 15 over 2 pi squared, and then 1 minus x squared. So this is a polynomial, all right? And by some computation, this cube x can be written as follows. I think I will end here. So you can also verify this at home by plugging into some solver devices. This kind of computational example to get a feel of what's going on. Now, let me end this video by a remark. And then the remark is as follows. This is the remark. If we have a vector space which is finite dimensional and a linear functional, okay, V here finite dimensional, and here we get a linear functional from B to F, of course, linear functional, then we can express the linear functional as an inner product of V with respect to U and U for all V in the vector space V. And then specifically, you let we have our U here. We will write U as this one. The conjugate is a 1, E1 up to the conjugate of the linear functional of En. So here, this right-hand side seems to depend on orthonormal basis E1 to En as well as on the linear functional. However, in 6.42 tells us that U is uniquely determined by our linear functional phi. Thus, the right-hand side of the equation above is the same regardless of which orthonormal basis of V is chosen. So in this case, this is true regardless of what orthonormal basis of V is chosen. So it's chosen, but here we just have a procedure to get an orthonormal basis by a Gram-Schmidt process. But in case you already have an orthonormal basis, which is different from the one derived from the Gram-Schmidt process, but again, it's orthonormal and it's orthonormal basis, then the remark here in 4 point and 6.42 tells us that it doesn't matter. So this is unique. This vector is unique regardless of what, regardless, the keyword here is regardless of what orthonormal basis of V is chosen. Okay, so I think I'll end here. Riesz representation says that you get a linear functional on V is just an inner product with a unique vector for each there is a unique vector V such that your linear functional applied to vector V for each V in the vector space is just equal to the inner product of the V together with the unique vector U, wherein our U is expressed as a sum of the conjugate of the linear functional applied to the orthonormal basis multiplied, we have that as our coefficient, and then e sub 1 to e sub n, sum of basis elements. So I think that's all for this part. It's been a long topic because mostly it's sometimes computational, but let me end this. Finally, it's ending this lecture with the following remark on what's coming up next. Next will be orthogonal complements. And then we will have minimization problems. So we will define first orthogonal complement of U, and then we will develop the theory to get methods in solving minimization problems. Okay, I think that's all for today. Let me end the recording.